Cool. So welcome again, everyone. It's our great pleasure this month at our first seminar of the year to host Stephan Mandt. Stephan, he's an associate professor of computer science and statistics at the University of California in Irvine. Before that, he was a senior researcher at Disney Research and postdoc at Columbia and Princeton. He mostly works on Bayesian inference, generative modeling, neural data compression, and physics applications. And based on the title of his talk, I assume he's going to talk more about neural data compression today and why it hasn't quite taken off yet. And with that, I'm happy to hand it over to you, Stephan.
Yeah, thank you, Vincent, for the kind introduction, and welcome, everyone. So the title of my talk has already been announced is I Can't Believe It's Not Better, Why Neural Compression Hasn't Taken Off Yet. So what I'm trying to do today is I'll hope to try to provide an unbiased view on, or realistic view on, the field of neural data compression, highlighting both its current weaknesses and disappointments, but also perspectives for the future. Okay. So I'll start with how I initially got excited entering the field, namely to discover compression as a new playground for particular Bayesian machine learning and statistical machine learning more broadly. I will then talk mainly about challenges of the field to make it really practical, and finally also about the future of neural compression.
Stephan, I think we still see the title slide. I'm not sure whether that's intended.
Oh, no, that's not intended. Okay, there's something wrong here. So you probably have to redo. No, you see probably everything, right?
No, we see only the slide. Yeah.
Did it change?
Yeah.
Okay.
Cool.
All right. Right. So I'll talk about how I got excited about compression, the disappointments, and the future. Okay, so let me maybe motivate the field of neural data compression a bit. I mean, obviously, we produce a lot of data every year, and all this data has to be stored and compressed and transmitted. And on the one hand, we have a lot of traditional data types that are growing in quantity. For example, video streaming on the internet is accounting for about 80% of all consumer traffic. But then we also have exciting new data types for which no existing compression schemes really exist. And those, for example, include point clouds used in self-driving cars a lot, or, for example, 3D data for AR and VR content. To just kind of give you a couple of examples, let's dive a little bit into video streaming. As I already said, video streaming is very important. We're already using it as of now. While there's a lot of generic video content on the web, turns out that video streaming content is fairly low entropy, right? I mean, it's basically only showing a talking face, and you can actually fine tune a compression algorithm on that particular face, in some sense personalizing it. And this way you can really achieve dramatic savings in terms of bitrate while not suffering almost any quality loss in the video. So there are different companies who are already doing this, and generally, for example, NVIDIA achieved a factor of 10 of bandwidth reduction using these specialized codecs, for example. Now, this is only one example. Another example is, of course, LiDAR data that I also mentioned as a new emerging data type. These LiDARs produce massive point clouds that have to be compressed, oftentimes in the billions or tens of billions or even hundreds of billions of points. So, for example, there are point clouds of the entire Sierra Nevada. And as you can imagine, up to the fine-grained details of individual trees, all this data is, of course, massive, and we need dedicated compression approaches for those new emerging data types. So to kind of get everyone on the same page, let me start with a sort of fundamental view on neural compression. How does it work? And also remind everyone on, how does data compression work in general? So for now, let's think of data as points in a, for example, 2D space. And let's for now imagine that these data are discrete, so they live on a grid, or at least countable. And this setup allows for lossless compression. Right? So how does lossless compression work? Well, the first thing is we need a probability model over these grid points, right? Over these points A, B, and C. So assigning a probability value to every grid point. Let's call that probability model capital P. And the first thing we do is we evaluate the probabilities of these points on that grid. And now we feed these probabilities into what's called a coding scheme. For example, you can think of a Huffman tree. And this coding scheme will then assign bit strings to these individual events in such a way that frequent events, items that are likely are assigned short bit strings, and rare ones are assigned longer bit strings, such as to overall, optimize the expected code word length as averaged over the data set. Now, there's also lossless compression and lossy compression, of course, right? And so now, how is lossy compression different from lossless? Well, as the name already says, there's some information loss. And the easiest way to think about it is, some sort of truncation, for example, induced by rounding. So for example, you can here imagine that the data are now real valued. They're still living in this two-dimensional space. But when we compress them, we first have to truncate and round them to this integer valued grid. And once we've rounded them, we can then still losslessly compress the rounded data, right? So lossy compression is typically a combination of truncation or rounding and lossless compression afterwards. And there's one particular coding scheme that's probably the most important and widely used in industry, and that's called transform coding. The idea of transform coding is very simple. Instead of doing the rounding and truncation in the original data space, you actually do it in, you first transport the data, or you map the data from the data space into a latent space. There you do the rounding and entropy coding. And from there, you can then ultimately reconstruct the data by transporting them back into the data space. So this involves two mappings F and G, right? And this already very much looks like an autoencoder, of course, and we'll soon get to that autoencoder analogy in more detail. To come up with a unified naming scheme, and for the notation, I will typically refer to data in the original data space as X. The data in the latent space are represented by Z, and I will typically call the reconstructed data X hat, right? Remember, they come from first mapping X into Z space, rounding, and then mapping it back into the X space using the mapping G. So final part of the introduction, I want to talk about how we evaluate compression models. And typically, this is done by looking at two quantities, namely rate and distortion. Rate is just the expected number of bits that we use in order to compress a data point, right? And distortion you can think of as mean squared error, right? How much does the reconstructed data point deviate from the original data point in terms of mean squared error in the original pixel space? And those two quantities are typically looked at in terms of this rate distortion curve shown here, where, given one particular compression algorithm, every point here corresponds to a particular parameter setting, correspond to one particular pair of rate and distortion, and multiple different parameter settings of the same algorithm will then span a curve. And when we ultimately want to compare different algorithms, we have to look at their entire rate distortion curves. And naturally, you want to be in the very bottom left corner, because that's the point that corresponds to low rate and low distortion. But as we'll also talk about later, this is not fundamentally impossible to achieve, because there's something called a rate distortion function beyond which you cannot go, right? So there's this underlying trade-off between rate and distortion that we have to live with. But we are sort of looking for the best compromise. Okay. Okay. All right. Okay. So neural compression is all about learning compression algorithms from data. And an obvious question is, can we directly parameterize these encoder and decoder mappings F and G from transform coding by neural networks and just train everything end to end so that we have a fully data-driven learned compression algorithm? So here once more is this operational diagram. We go from data space X to Z space using F, then we round, that corresponds then to Z hat. And that's the space in which we have a probability model P. And from there, then we go back to data space X hat. Now, ideally, would like to minimize directly the following object. It's basically a minimization problem over the encoder, the decoder, and also the probability model P, which is also called an entropy model. And then the loss function that you'd like to optimize is an expectation under the data. And then we have a combination of two terms. The first one is the expected code word length that we would like to minimize, the negative log probability of the rounded encoded data, and then plus lambda, a weighting factor, times the expected distortion, right? The distortion measure rho between the original data x and the reconstructed data g of f of x. But there are two problems with that, right? We cannot easily differentiate this loss function directly because, first of all, quantization is not differentiable, right? We cannot backpropagate our gradients through this operation. And then also the entropy model is a discrete probability model, right? Remember, living on a discrete lattice, and that's also not differentiable with respect to its input. Now, there's a nice workaround that has been proposed by Johannes Ballet like about 5 years ago, and it's been very popular since then. And the idea basically is to replace rounding by injecting uniform noise, right, centered around 0. So and with a support of between -1/2 and +1/2. So we just inject noise into our latent representations. And the basic idea behind that is that, you know, this roughly corresponds to the empirical noise distribution that emerge that corresponds to the truncation step, right? So the residuals that we truncate would roughly follow this distribution. The second idea of dealing with this not differentiable entropy model is also very elegant. So instead of optimizing a discrete model on the discrete grid points, we just relax it to continuous, and then we can actually compute the probability mass function, the cumulative probability of that continuous probability density, and evaluate it only on the grid points, right? So this extends the probability mass function P to real values. And this can also then be parameterized by neural networks and learned end to end. The resulting objective then looks as follows. We have, again, the same expectation as before. And yeah, we have negative log small p of f plus u, u is this noise variable, plus lambda times the distortion between x and g of f of x plus u. Okay. Now, it turns out that this is, of course, very related to what we know as variational autoencoders. And let me actually highlight that connection in more detail. So what do we do when we train a variational autoencoder? Well, first of all, it's characterized by two operational diagrams, right? The first one is sort of how we go from X space to Z space. And there we typically first encode a data point X deterministically using some function F. And then we add uniform noise to that, which results then in a random variable Z twiddle. And this, of course, then corresponds to a uniformly distributed variational posterior centered around the mean encoding F. When we generate data, we sample it from the prior p-tip p-twiddle. And from there, we push it through a decoder network G. And ultimately, in the last step, we add a little bit of noise to that, typically Gaussian noise. And let's imagine that this noise has a standard deviation sigma. And when you write down this elbow objective, we write it down as follows, just following variational inference. And the important observation here is that the entropy term is dropping out. And the reason is that, remember, Q is a box-shaped distribution, so that actually has entropy 0, so that evaluates to 0. And so we're remaining only with the first two terms. And then if we apply the reparameterization trick to optimize this objective, it turns out we arrive, you know, with exactly at the same loss function that we had on the previous slide. So you can think of this as a rare coincidence, but there were indeed two different communities back in 2017, one coming from the image processing side, and then, of course, the variational inference community. And they just learned about each other around like 5 years ago. And since then, there's been a lot of interesting crosstalk, and Bayesians in particular being interested in the field of neural data compression, which was in particular also my own trajectory, how I got interested in the field. Namely, historically speaking, back in 2018, 2017, you know, I worked on particular a relatively simple model for learning disentangled representations in videos. We were trying to disentangle motion information from content information such that we could independently generate a video that had the same content but different dynamics, or the same dynamics and different content. So we came up with that particular graphical model that you see here on the top of the slide. And then learning about these neural compression techniques, we actually immediately converted that into a video compression model. The idea being that, you know, you can compactly store global information in one latent variable and dynamic information into a series of time-dependent latent variables. And the result of that was actually one of the first neural video compression papers ever published. I think it was something like paper number 3 or 4. Now, arguably, I don't want to spend too much time on that because it was like not very scalable. It used fully connected architectures, and we only exported on thumbnail videos. So maybe not that interesting, but definitely for me, an important first step. And later on, we continued working on this and went to the more impactful work on video compression, where we looked at how the compression community is currently using neural networks in terms of compressing video. And then we came and came up with all sorts of innovations from variational inference and generative modeling that we adapted and actually improved the performance of these existing algorithms, right? So on the left-hand side, you see a particular video frame showing different extensions of an existing neural compression approach, making it better by essentially adding temporal priors, adding dependencies between latent variables, and also borrowing on ideas from autoregressive transforms that were invented in the image community, in the image generative modeling community. On the right-hand side, you see the resulting rate distortion curves. Okay, so this was all the exciting part of it, but let's actually come a little bit to the disappointing aspects. So let's step back for a moment and consider the status of the field as of today. I mean, first of all, it is generally true that neural image codecs have beat most non-learned image codecs at this point in terms of rate and distortion. And so what we did here is we evaluated many of those proposed methods on a common benchmark. And this looks roughly as follows. So on the left-hand side, you see, again, another rate distortion function. But this is actually rather a quality rate function. Namely, the left-hand side is actually a PSNR, which is a quality metric. So higher is better. And the x-axis, that's the rate, right? And so the rate distortion trade-off is here displayed by just essentially monotonically increasing curves, right? As the quality goes up, so also the bit rate has to go up. And what you also see here is that there are several recent baselines on this plot. And what's slightly concerning is that these gains seem to saturate, right? You clearly see that people have tried harder and harder to beat rate distortion performance, and it's getting harder and harder to getting these papers published because essentially the gains are vanishing over the years. So this is slightly concerning, of course, and you might wonder why that is, right? I mean, could it be that we're just hitting a fundamental limit that exists that just prevents us from getting further beyond that limit? And the answer is unfortunately yes, such a limit exists, and it's and that's called the information rate distortion function. But without knowing the information rate distortion function, we cannot really know if we are already at this point. So let me actually discuss a little bit about that in a bit. Now, that's only part of the disappointment. The other half of the disappointment of neurocompression is that it is about runtimes. So here I'm actually borrowing slides from David Minnen, one of the leading researchers at Google in data compression, and he kindly offered that slide to me. So one way of looking at different codecs is to not look at rate distortion, but rather to look at to fix the bit rate and then plot the existing algorithms in terms of the trade-off between quality and runtime, right? Distortion and runtime. And that's shown exactly here. So on the x-axis, we have flops as a measure of runtime. And on the y-axis, we have, again, PSNR as a measure of quality. And as the intuition would tell us, if you're investing more compute, then your models get better and the quality increases. But unfortunately, there seems to be, again, this fundamental trade-off, which is not really proven at this point, but which is clearly evident. So here, all the points are models from different proposed architectures, and the scatter points vary in terms of the architectures themselves, right? So some of them have like convolutions that have broader, like larger receptive fields than others, right? So we have parameter richer versions of these proposed models and ones that are more parsimonious. Now, you see that I'm not only showing these Google experiments showing neurocompression models, but there are also these dashed lines, which are horizontal. And for those algorithms, we don't have the corresponding flop counts. But what's slightly concerning is that VTM, a classical algorithm, reaches actually a pretty high degree of quality at the same bit rate as all of the other models that are displayed here. And in particular, if you now look at runtimes, you see that like at this particular level, a popular architecture from neural compression reaches about 0.2 milliseconds. And of course, these runtimes explode as you go to more and more powerful neural network-based architectures, actually to a degree that are not acceptable anymore in industry, right? Some of them take a minute to decode an image, and those are relatively small scale images. But VTM, a classical algorithm, is actually much faster than all the neural algorithms considered here at the moment, right? And that's definitely concerning. I should say also that encoding in this algorithm is pretty slow, which is a different dimensions, but for now we're mainly concerned about decoding times. Okay, so when I saw that, I found those results pretty sobering. So you see Richard Hendricks here from the HBO show Silicon Valley, a founder of a fictional compression startup, looking disappointed. So neural compression is currently an order of magnitude slower to be competitive with classical codecs. And furthermore, we've seen diminishing returns as we work towards increasing the rate and distortion performance. And there are actually all sorts of other obstacles that I didn't really talk about here and don't have the time to talk about. For example, it's very hard to change a running standard in the industry, as you can imagine. There's resistance to changing a running system, and there are all sorts of other issues that exist. But being an optimist, I want to discuss here if all of these downsides are really as bad as they seem, right? And so I want all of us to take a closer look and maybe discover the regimes in which neural compression can still have like really interesting and big impacts in the future of technology. Okay, let's take a closer look at the rate distortion function for now, right? As I told you earlier, there's this fundamental information theoretical quantity called rate distortion function. And the rate distortion function, first of all, is only a property of the data set and a property of your distortion metric. It has nothing to do with any particular compression algorithm. And in particular, the rate distortion function, the information rate distortion function, tells you what are the possible bit rates and distortions that an algorithm can achieve, and which pairs of rate and distortion are simply impossible to achieve. And formally, it's defined as this complicated mathematical object shown here. It's a minimization over mutual informations between inputs and outputs over some stochastic encoder subject to a certain distortion constraint. Before we go more into detail, let me show you what the rate distortion function is doing. Again, giving pairs of rates and distortion, this rate distortion function would essentially learn a decision boundary between regions that are feasible and regions which are fundamentally impossible to achieve. Right? All right. Now, the important part is that this rate distortion function is actually not analytically available, only in very special cases, namely when the data distribution is assumed to be Gaussian, then information theorists have sort of worked out certain solutions. But anything beyond that is completely intractable and unknown to compute, and also very difficult to optimize, as we see in a moment. So instead of learning the rate distortion function or estimating it, we had a different idea, namely we wanted to learn sandwich bounds on that rate distortion function. Particularly, we wanted to learn upper and lower bounds. The upper bound is basically a possibility result, right? If something is above the upper bound, it tells you, this point in rate distortion, in the rate distortion plane, is definitely achievable, should be definitely achievable. Whereas the lower bound, the red curve, is an impossibility boundary, right? Anything below that lower bound is for sure not achievable. And ideally, you want to of course, learn very tight bounds so that you really sandwich that rate distortion function to get the most information out of your analysis. So how do these bounds work, and how do they connect to, again, Bayesian deep learning and variational inference? So we published that in a recent iClear paper last year, and in fact, we worked on both the upper and the lower bound. And let's first talk about the upper bound. So it turns out that these rate distortion upper bounds can be achieved by beta variational autoencoders, right? So maybe you first think this is not surprising, because we all know that if you change beta in a VAE, that really spans a rate distortion curve, right? Maybe it's not that exciting, but the important part here is that this is a result independent of any architecture, right? It tells you that if you take any VAE and you look and you train it at different bit rates, and then you take the envelope of all possible VAE models that you used, the resulting envelope is going to be an upper bound on the information rate distortion function of your data set. Right? And so that's kind of a nice result. For more details, I refer to that paper. The other result is much more complicated and not all positive, and we'll get to that later. So it turns out the lower bounds are a very nasty object mathematically, and also in terms of optimizing them. So basically, first of all, how did we get these lower bounds? Well, we used Lagrange duality. Right? If you write the Lagrangian dual of an objective function, it typically amounts to a maximization problem over an infinite dimensional space. And then you can make that maximization problem finite dimensional by restricting the space. And the way we restrict the space is that we parameterize the emerging functions that we minimize by neural networks. Right? So this kind of gives us a lower bound to the RD function. But the problem here is that there are all sorts of constraints that have to be respected. And again, it's very technical. And if you're interested in that, I'll refer to that paper. Okay. So let's see how useful these bounds are. And let's actually start slow and start with low dimensional data sets, and then slowly approach our more realistic high dimensional data sets. So the first data set that we looked at is actually a particle physics data set. So here we look at collision events coming from another project where sort of two particles collide, their momenta and energies mix, and then they spread apart. And basically we look at the summary vector of that collision event, which is 16-dimensional. And of course, all these dimensions are highly correlated, and some of these correlations are shown here in the scatter plots. Now, if you look at this data set and computes its upper and lower bounds to the information rate distortion function, in other words, trying to evaluate its lossy compressibility, we actually arrive at this shaded red region that you see here. Right? So light red is our upper bound, and dashed dark red is our lower bound. And to check if this is a trivial or non-trivial result, we trained a neural compression model, one of the best availables on that data set, and like the operational rate distortion function that we got from this particular compression scheme lies above the upper bound, right? Which tells us that sort of our upper bound learns something non-trivial, right? It's basically something that an existing compression scheme has not achieved yet. Now, in order to validate it, we have to compare it against a numerical method that can actually compute the rate distortion function. And I was not completely clear earlier that I said that no existing methods exist. It turns out that there is an exponentially scaling algorithm called Lahut-Arimoto that works in finite dimensions that are discretized. Its complexity grows exponentially in the data dimension, which is not very scalable, but in 2 dimensions, we can actually apply it. And we see that the actual 2-dimensional rate distortion curve indeed is contained in our sandwich bound, right? Which is kind of reassuring. We can also go to higher dimensional data like acoustic data. Don't want to spend too much time on this, but those are 33-dimensional, and you see that again, similar findings. We sandwich the rate distortion function. It's a non-trivial result when comparing it to the blue curve, and but the difference is that the bound or the region of uncertainty grows relative to the lower dimensional setup, right? And that's slightly concerning, and we'll go back to that. And finally, what we could also do is we could look at a artificially generated data set of GAN-generated images, where we had explicit control over the real intrinsic dimension. So what we did is we took a pre-trained GAN or a trained GAN, and we fixed all the dimensions in the latent space of the GAN except 2 or 4. And then we sampled only in the subspace and generated images, right? And in this case, that generated all sorts of dog images that shared a lot of similarities. But this is a real image-like data set of dimension 128 by 128 and 3 color channels. But note that its intrinsic dimensionality is really 2 or 4. Right? And for those data, again, we could compute upper and lower bounds. And they're non-trivial. And in particular, you can now really see that on those data sets, the existing compression methods are way above the information rate distortion function that we identified, right? Which is a sort of optimistic result. Although, again, those are not real-world image data sets. Those are sort of GAN-generated images. Now, why did we do this? Why didn't we do this for real-world images? Well, the thing is that while the upper bound scales very nicely, it turns out that the lower bound doesn't scale very nicely at all. Right? It's really only working up to a couple of hundreds dimensions, and anything real world, natural images, the bound essentially becomes flat. Right? And so what that means is that we can reliably estimate the upper bound of the rate distortion function, or at least we get some scalable results for that. But for the lower bound, we basically have no good results in higher dimensions. And you can either think of that as a positive or a negative, right? It's a negative for our method, but it could be a positive because there could be potentially still a lot of gains to be harvested. Okay, so let's revisit the plot that I showed you earlier. And in addition to these existing compression schemes on the quality rate plot, I'll also add for now this fictitious rate distortion function that we don't know where it is, right? But what we did achieve is we could actually estimate the region a little bit better than before, right? So what you see here in blue is basically our bound to the rate distortion function, telling you that it is at least as far away as that. It could be higher, but it is definitely higher than the blue curve, right? So at least we can gain another 1 decibel for all the existing compression schemes. Yeah. Okay. Yeah. So that's yeah. Okay. So in the last few minutes of this talk, I want to talk a little bit about the future and how to deal with these sobering results, or in part sobering results, that we've encountered in earlier parts of this talk. So I will try to be optimistic here and present several future directions for compression research. And there are different directions that we can try to go into. The first one is to accelerate neural decoders. And one idea to do so is essentially to exploit an asymmetry between encoding and decoding, right? So if you think about it, right, Netflix, if you want to develop a new video compression codec, right, they might have like maybe hundreds of thousands of movies, but they certainly have hundreds of billions of viewers who all view movies many times, right? I don't know how many, I didn't do the counting, but let's say, every user, like every movie gets watched 1,000 times, or maybe much more. So this essentially means that you have a much larger budget, a time budget to spend on compressing or encoding a video than you have on decoding it. Decoding has to be really fast, but you can actually spend all the time in the world if you want to for encoding your video content, right? You can spend a weekend on that. Shouldn't be a big problem, I guess, right? So definitely these asymmetries exist. And you could exploit them either by asymmetric architectures or by asymmetric coding schemes. And this is visualized here. On the left-hand side, we have a symmetric autoencoder, which uses amortized inference, right? Its encoder and decoder are equally powerful. And on the right-hand side, we have a heavily distorted autoencoder, which has a very powerful encoder and maybe a very shallow decoder. And at the same time, we can also do something more time-consuming for the inference part, right? Spending more time on inference, learning a more compact, more compressed latent representation. And that will also accelerate ultimately, or that will lead to better performance even for shallow decoders, and therefore ultimately solve our timing problem. So what do I mean by that? So this actually refers to older work in my group and also relates to work of others. So it turns out in variational autoencoders, as many of you know, I guess, there's something called the amortization gap. And the amortization gap essentially means that training an autoencoder or a variational autoencoder using amortized inference is only an approximation that's fast and scalable, but you get actually better results if you learn each data point's individual encoding, its own variational posterior by optimization. Right? So you can basically optimize the mean and standard deviation of every individual data point in that latent space. And this is actually this was proposed by multiple groups, including ours, by Marino and others, around the same time. At the bottom, you see, like a fictitious latent space where the red dot is the global minimum. The green dot is basically what an inference network would get you, and the blue curve is what an optimization algorithm would find. Right? And so the inference network already does a pretty good guess, but you can actually do better if you spend more compute and refine the latent representation, find a better optimal. So one of our achievements here was to actually translate that work into the world of neural compression, and propose this amortization gaps and ways to close it. Turns out there's already some preliminary work on that, but we could actually significantly improve it with the next trick. And the next trick was to also discover what's called the discretization gap. Now, what's the discretization gap? The discretization gap is an inefficiency in the learned compression approach. Namely, on the one hand side, you train your model using noise injection from a uniform noise distribution. But when you then deploy the model, you round, you discretize. And obviously, those two things are completely different, right? And the difference in performance between your test elbow and your training elbow is actually called the discretization gap. Now, how can you close this gap? Well, you could either, from the beginning, try to learn the discrete representations, and some people have tried that, but you can also do something simpler, namely you take a trained VAE, and then you do a discrete search at test time. Right, you kind of search for a more compact latent representation of any new data point that you're trying to encode. Spend a little bit more compute on that. And this discrete search can be elegantly done with a technique which we call stochastic Gumbel annealing. Right, it's basically a gradient-based search method that uses the Gumbel softmax trick, and that ultimately ends up at a discrete lattice point, which has a better trade-off between rate and distortion than the initial point that your inference network gave you. And that search path is illustrated here in the plot. Now, this paper also had a third contribution that I don't really have time to get into. It's called the marginalization gap, and it has something to do with the fact that in compression, you actually don't use shallow variational autoencoders. You typically use hierarchical variational autoencoders with multiple latent variables, typically 2 levels of latent variables. And you want to integrate out the top level latent variable to learn essentially a very powerful prior on the lower level latent variable. But since you cannot integrate it out, you have to estimate a lower bound, and the inefficiency that's resulting from that, we call it the marginalization gap. And it turns out that this marginalization gap can also be closed using a technique called lossy bit-spec coding, but I don't really have time to talk about it. Okay. Yeah, how well does this method work? Let's look at the rate savings that emerge from that. So rate savings means the x-axis here are different quality levels, PSNR, and the y-axis is the relative reduction in bit rate of a given method relative to a baseline. And the baseline here is BPG, which is a very modern and well-working classical image codec. And now what you see here are different curves from different neural and classical algorithms. But the important part here is we applied our discrete optimization on a given trained model, which is the Brown curve, which is Mandt et al. 2018. And then using our techniques without any training, just as a test time, raise or reduce the bit rate by a factor of 15 to 20% in this given architecture, right? Which is quite remarkable. I should say that this takes about 100 times longer, right? So if you have a minute to encode a video, of an image, right? You should do that. You find a better compressed representation. If encoding has to be fast, right? Then you cannot really do that, right? But this is one example of this asymmetry that I talked about earlier. That with a little bit more compute at encoding time, you can actually learn a better rate of distortion, such that you can eventually afford a less powerful and therefore cheaper decoder. So that's the main idea. And now also, this is actually visible when you take a little image patch and apply the Gumbel softmax annealing trick to that. You'll actually get visibly better qualities for that particular image patch. Okay. What are some other ideas? Another idea is to make decoders faster using more lightweight, more parsimonial models. So most research right now has focused on optimizing rate distortion functions, right? Irrespective of any restrictions on compute. And the result of that was, of course, heavily expensive parameter-rich models that were in part intolerably slow, as we saw, right? Some of the most recently proposed methods take a minute to decode an image. And then instead, I and other experts in the field argue that this focus should rather be more on lightweight models for faster inference to make them practical and compatible with existing classical methods. And for that, we need to sacrifice some of the rate distortion performance. And just as one idea, you could actually draw inspiration from simple linear models such as JPEG, which is actually a particular form of a linear autoencoder. So what it does is it takes an image, it's first transforming it into a rotated space using sort of essentially a color brightness channel and two relative color difference channels called YCC transform. And from there, it extracts DCT features, discrete Fourier cosine transform features. Then it scales up the corresponding elements to account for different quality levels. And then it's applying the truncation by rounding, right? And then you can actually undo all of these steps except the rounding step to reconstruct your image. So it's basically a linear, non-learned autoencoder. And there's recent evidence that actually suggests that the current neural compression models implicitly learn very similar features or feature maps as these DCT transforms, right? And that has something to do with the fact that the receptive fields of the compression architectures are relatively small, right? And maybe that could also be like a starting point for some further digging and exploration for more efficient architectures. There's also another path, which I found pretty exciting, which is on improving entropy coders. Remember, the priors are also learned models and can be potentially expensive. And as one potentially much cheaper architecture, we teamed up with some experts in probabilistic circuits, which is a sort of particular niche area within machine learning, coming in part from the more sort of AI side of things. And it turns out that these models are now getting better and better, and there are also tutorials at major conferences on these models at image generation, and therefore also density estimation tasks, while at the same time being extremely lightweight and fast, right? And so basically what they do is they are essentially mixture models. So they correspond to, they're sort of combining different pixels by weighting them and building sums and products of different patches and integrating this into a hierarchical architecture that allows for linear time inference, meaning linear in the pixel dimensions. Right, so this can be potentially very fast. Yeah, and what we showed here is that we can actually also get a factor of 10 in runtime reduction over very expensive models, such as, for example, discrete normalizing flows for lossless compression that were proposed, while at the same time achieving comparable bit rates. And the last but not least, very important area of future research is that focusing much less on distortion, but much more on perceptual properties of images. In other words, perceptual compression. So remember, what do we expect from an image codec? We certainly want to have a low bit rate. We also want to have a low distortion, but overall, we want the reconstructed images to look good, to look realistic or convincing to us, right? And it turns out that low distortion is actually not the same as good perceptual quality. And to illustrate this, I'm showing here a plot taken from a blog from NYU here on the right-hand side, where you have different images of Albert Einstein that were perturbed using different kinds of noise and blurs. We have the original image, then we have a slight spatial shift, then we have salt and pepper noise, Gaussian blur, and JPEG decompression. And you see all of those look extremely different, right? But at the same time, they all have the same mean squared error, which is very surprising because the spatial shift is barely noticeable, which means that mean squared error is a terrible metric for detecting spatial translations, and which could really raise doubt on whether this should be really the only quantity to pay attention to. All right. So what have people proposed already? So there's one particular exciting development, again by Google, called the Hi-Fi-C paper. So what is Hi-Fi-C doing? It's essentially what the generative modeling community called a VAE-GAN or VGAN architecture. So you take a variational autoencoder with a reconstruction loss, but then you also add an additional GAN loss to that. And the GAN loss will basically compare the reconstructed image with any given image in the data set without reference to the original image. And it turns out that these two losses together correspond to a different trade-off that I'll talk about later. But with this additional GAN loss, you will actually get much better perceptual quality. So what you see on the right-hand side is an image divided in half, where the left-hand side is compressed using Hi-Fi-C, and the right-hand side is compressed using JPEG, where JPEG actually had twice the bit rate while having at the same time a much more blurry reconstruction than the left-hand side. Right? So this is kind of pretty exciting results. And of course, you can also achieve similar things with diffusion models, and there's some ongoing research in this direction as well. Now you might ask, shouldn't distortions already take care of perceptual qualities? Isn't that sort of the same thing? And the answer is no. There's this very interesting, exciting theoretical work by Blau and Michaeli, who actually showed that there exists something called the perception distortion trade-off. And in fact, that doesn't only apply to compression models. It actually applies in sort of generative modeling more broadly. So it turns out that these two different terms, adding an adversarial GAN loss and having the reconstruction loss from a VAE, they necessarily exclude each other. They compete with each other in the sense that you cannot at the same time have like perfect distortion and perfect perceptual quality. Yeah. And so if you're interested in more details, this is actually explained in the paper that I'm highlighting here on the slide. Okay. So what does this tell us? It basically tells us that when we evaluate lossy compression methods, we should not completely abandon PSNR and mean squared error, but we should be much more conscious of these inherent trade-offs. We should actually look at multiple metrics. Mean squared error is still an extremely useful debugging tool for training these models, and it's also one of many metrics that we should care about. But ultimately, it shouldn't be sort of the holy grail, right? I mean, we definitely have to evaluate models using a multitude of different perceptual metrics as well. Okay, so this gets me to the summary of my talk. So I talked about neural compression, and we found that if you put computation aside, then neural codecs are certainly better than classical codecs, right? But when we introduce computation and runtime constraints, then neural is currently not competitive with a traditional codec. So it's very difficult to reduce the flops without sacrificing some of the rate distortion performance, although this is actually, to my knowledge, an unproven fact and more like an empirical observation. We also, it's not that neural compression is 10 times better than anything that exists. It's actually much more subtle than that. But it's actually hard to understand why. It might be that at high quality levels, if you look at only patch-wise image statistics, that these image patches actually do look pretty Gaussian, and then we would have theoretical results why something like linear compressors are optimally suited. But certainly for larger images and larger patches, this is no longer guaranteed. Yeah, but at the same time, framed positively, this actually enables new possibilities with parameter efficient architectures. At the same time, we talked at the end about rate distortion plus realism, and there is actually a lot of gains to be expected still. So those models clearly have an advantage over traditional codecs with lots of promise, and in particular when the hardware will catch up such that we can really compare apples to apples and not kind of compare models with dedicated specific hardware which have been around for decades with neural models that are operating on GPUs. And finally, there's a lot of promise to compress non-traditional data types, for example, point clouds, 3D models, overfitting models to individual users or to long videos. So I think there's still a lot of unconventional compression where there's significant gain to be expected in the future as our data formats and needs will change. So with that, I'm done. So thank you very much for your attention, and I'm here for your questions.
Cool. Well, thanks a lot, Stephan. That was a very interesting talk with a lot of material to cover. Yeah, if anyone has any questions, please write them in the chat, and I'm happy to read them out. Maybe I can start with a slightly silly question, probably. But when you showed us these upper bounds that were computed using some beta VAEs, can you? I mean, essentially, what I'm wondering is, can you just use these beta VAEs then to actually encode the content, because they seem to give better quality than most of these codecs, right? Or is there something that makes them actually a bad compression model?
Yeah, that's a good question. So maybe coming back to my earlier talk, right? I showed this analogy between compression models and variational autoencoders, right? It turns out that in the approach I talked about, this ballet style encoding approach, which is sort of mainstream nowadays. You only have this analogy if your variational posterior is really box shaped. In other words, it has variance 1. So the variance is not a learnable parameter. It's set to 1 because it's sort of mimicking the rounding operation at training time. And only then you can really, with these tricks, you can really use variational autoencoders for actual compression. Because if you just take a variational autoencoder and you sort of encode an image, your latent space is still going to be continuous, and there's no obvious entropy coding scheme. I mean, maybe you could kind of discretize the VAE in hindsight, right? Maybe doing vector quantization and things like that. So that can certainly be done, but then again, you have this training and testing mismatch that the algorithm wasn't informed about the quantization at training time. So it's not obvious how to use standard VAEs for compression. That said, we actually do have a paper that does something like that. But we found that while it's very promising, it doesn't really compete with these learned end-to-end methods, at least not on the typical rate distortion performance, because the VAE types of compression models, they're directly optimized for rate and distortion. And any other model that you come up with is not optimized for this trade-off. And so it will look worse on this particular metric. Yeah, hopefully that addressed your question. Yeah, thanks. That makes sense. Since there are no other questions right now, I'll just indulge myself and ask another one. So yeah, you said essentially the runtime trade-off with a rate distortion is a problem, right? And so given that you said there's this algorithm to actually compute the true rate distortion curve in exponential time, I guess that might mean that you could also reach optimal compression in exponential time, but presumably maybe you don't want that because it's too expensive. Like, are there similar bounds for kind of given complexities? Like, can you say like there's a maximum rate distortion you can reach within linear time or polynomial time or log linear time or something like that? Or is that kind of open research question? Yeah, I might. Yeah, I'm not familiar with any of this. Those would be certainly very relevant questions, but I'm not sure that there's already existing results on that. I could be wrong. Yeah, but about the optimality, I mean, yes, I mean, it turns out there are always very expensive coding schemes that sort of reach optimality, as you correctly said. One of them is sort of, for example, vector quantization, which is basically a glorified version of FK means, right? I mean, if you have essentially unlimited training data, you could basically cluster the data into a huge number of clusters, and but such a way that still every cluster has like a large number of data points assigned to them. And then if these clusters are lying dense, you can actually use these clusters as a density approximator, right? And that approaches optimality if you have sufficiently many data points and sufficient compute to actually do the clustering. But this scales terribly in higher dimensions. Which is actually why vector quantization is not really done, which is why people nowadays mostly do, almost exclusively do transform coding. Yeah. Cool. So Fran had a question on the chat. I don't know, Fran, if you want to unmute yourself, or should I read it?
I can read it. So essentially, well, first of all, thank you for the talk. It's very nice. Yeah, I mean, it's another silly question, just because I'm work on this area. So essentially, it's about you mentioned this kind of perceptual distortion metrics that sometimes might be, I don't know, more like behave very differently to MSE. No? And then, so my question is for non-image data sets or also non-audio. Like, what's the equivalent of that? Do we have some metric? I don't know, for other types of data, like the ones you were interested in. Yeah, great question. Yeah, first of all, there are lots of sort of perceptual metrics that have been proposed. So a lot of them actually rely on a pre-trained network, for example, an inception net that sort of takes images as input and maps them into like a lower dimensional space. And then in the lower dimensional space, if you do a comparison to the original image, you can either do the comparison in that lower dimensional space, which is sort of more semantic, or if you do a distributional comparison, you can basically evaluate the likelihood of an encoded data point in this lower dimensional space compared to a Gaussian approximation of the encodings of the data set as a whole in this space,
right? So yeah, so the idea is always that you need some sort of feature extractor and then do some simple geometric comparisons in these more semantic spaces. At least that's one popular type of doing it. And I guess if you had like other data, you could basically do that as well, right? For achieving perceptual quality for other types of data, yeah, I guess you can still do the GAN loss trick, right?
Yeah. I mean, I understand that
yeah.
if you do it implicitly, then,
right.
then you can do that for it. But I just curious what people use in okay.
Yeah, and then there's not only so those are called non-reference metrics, right? When you compare an image with any other image, just for does it look like being taken out of a certain data set? And then there are also certain reference metrics which really do the comparison with the original image, and those could be just mean squared error. But there's also lots of work on designing better metrics that are more semantically meaningful. For example, there's this SSIM metric, which is inspired by human perception on how we perceive contrasts and things like that. And you can directly optimize these alternatives to mean squared error to get more pleasing results as well.
Great, thank you.
Well, I should say, just in a bit of advertisement, there's going to be a IIII tutorial on compression, and there was last year a NeurIPS compression tutorial that I wanted to point out. If you want to learn more about this, there's also a compression review article if you just Google it.
Cool. Yeah, nice. We could check that out. I had another question actually regarding kind of distribution shift and OOD stuff. So I guess JPEG would, just compress all kinds of natural images decently well. But maybe if you train your compression on a specific type of image data, I don't know if you train it on classically images of cats and dogs or something, and then you show it a different image that's a different object, would it typically still work okay, or do you have these cases where it might catastrophically fail and just not compress well at all?
Yeah, those are great research questions. So actually, some of them I tried attacking myself, but kind of lost track on them, and I think other people have worked on some of those already. So long story short is, yes, these problems might exist, right? I mean, you definitely see sometimes in extreme compression regimes where like a phase would be, decompress into a generic phase, right? So that can happen. In fact, it can happen particularly if you have these, additional GAN losses, but it can also happen for autoencoders. That said, there's one aspect that makes these approaches a little bit more robust to this, namely, in order to be able to reconstruct images really well at high quality, we need large latent spaces, and we use convolutional architecture. So we preserve a lot of the locality in these latent spaces, and the convolutional architectures have relatively small receptive fields. So you kind of still preserve a lot of locality, and also the model picks up only sort of patch level statistics in the end. And I would argue the more local the statistics are that the model picks up, the more the more easily it generalizes to other data sets. And also we see that in evaluation, because usually we always train on one data set and then we test the trained model automatically out of distribution on other data sets. So in some sense, we all, the community is already doing the out of distribution testing. Yeah.
Cool, thanks. Yeah, it seems like there are no more questions on the chat right now. So in the interest of time, maybe we can stop here, but thanks again for the talk. That was really interesting. I'm sure many people will now check out all the tutorials at IIII and NeurIPS. Yeah, for everyone who joined today, thanks for joining. As Manuel has posted in the chat, feel free to join our mailing list to be kept up to date, and check out our website for the upcoming talks. And thank you, Stephan, for the great talk, and hopefully see you all at the next installment of the seminar series.
Thank you. Thanks for having me.